Hi, everybody. Thanks for having me. This talk is about Postgres indexes. It's an introductory talk. The goal is to understand more the internals, the features, and the different index types so that we can build better applications knowing how to use the appropriate indexes, not just throwing indexes at every field, but thinking about the query patterns, the data distribution, and what indexes have to offer us. Let's start looking at some examples, analyze how they behave under queries with indexes and without indexes, and then let's take a look at the internals of the B tree, of the indexes, and see how what changes when we use it and when we don't. So here we have a table of players. It has, we can see the schema here. It's just an ID and a name. This table has almost 1 million players. And we have also some special players here that we're going to search for them. And if we just select some specific player without indexes, we can see that the execution time is 265 milliseconds. And the main thing here I want you to understand and to pay attention is the buffers part over there. It shows how many pages were read from the heap. And I'm using explain analyze here, so this is actually running the query and collecting the costs. I'm also using buffers to show the actual number of pages read. This is something that is required for Postgres 17 and under, and it's very useful. You should use it, because indexes is about optimizing reads. Of course, we care about performance, but the main thing here, we are optimizing reads, minimizing pages read. So here we read a bit more than 6,300 pages, some from disk and some from cache. And we had to scan the full table. We did a sequential scan. It's a parallel sequential scan, but still a sequential scan. And we checked every row of the table for the player we're looking for. And we can see here that we filtered 1 million rows. It's written 3 million here, but we have actually 3 loops. And we had to read everything just to find one player. When we use an index, things change considerably and they improve a lot. We can see now that we're reading only 4 pages and the execution time is less than 1 millisecond. So this is a huge performance gain, and it's all thanks to indexes. And this index we're using here is a B tree, and I'm going to show you a simplified version of the B tree later, but first, let's understand how Postgres stores things in the disk and understand better the concept of pages and the CTIDs. So this is a schema, a diagram of a simplified illustration of how the files are stored in disk. We have a relation, and this relation has files called forks. Some of these forks are metadata, and the main fork is where the data actually goes. This fork, it can be split into several segments. The segments, they have 1 gigabyte limit. So for example, if we have a table with 16 gigabytes, we're going to have approximately 16 segments. And the segments themselves, they are also split in pages. The pages have a size of 8 kilobytes, and we have like an array of them inside each segment. Inside the page, it also has its own structure. It has like some headers. It has pointers to the tuples, the tuples themselves, and every tuple is identified by a CTID. The CTID is a pair of numbers. It will, the first number will indicate the page ID, and the second number is the offset of the tuple inside that page. So coming back to our example, if we select from the players table and we add, if we explicitly add the CTID here, this is an eternal Postgres field, but we can actually see what's going on there. If we add it here, we can see the CTIDs. And this is important for our talk because the index is, the CTID is the address of the row on the disk. And the indexes, they will map the indexed values to the CTID. So we can take shortcuts. We can, instead of looking the whole table, we can go to the index, find where the CTID is, and then go there. This is a simplified version of a B tree. This is what is responsible for the whole indexing magic, and it's a very interesting and powerful data structure. It's a balanced tree, so the distance from the leaf nodes is the same for every item, and we can do very quick lookups on this tree. It's a log n performance, like algorithm performance, and because of them we have like these huge speed gains. They are organized in a way that it's pretty, it has some properties, like for example, to find something on the tree, you will perform some very simple actions of finding where the item is and then following the pointer to nodes on lower levels, or finding the item between the, if what you're looking for is not this BR here, for example, you're going to find something between this and the smaller item. So it's pretty quick. Every time we go lower the one level, we are cutting half of the search space. And this is, it's wonderful, right? It's lets us search things really quickly, but it has some costs. Here, also important thing, at the end of the tree, the lowest nodes, the leaf nodes, they are pointing to the heap, to the address of the rows on the heap. And they're also ordered. On the tables, we don't have any order other than the insertion order, but here we can order according to smallest to biggest values. So when I say the heap, I'm meaning like where the data lives on the disk. So the index is separate from the heap. It will keep references to the heap. So yeah, B trees are great, and they are helping us to search data faster, but they have many hidden costs that we have to have in mind when working with them. There is a disk usage cost, because they can become pretty big, sometimes even the same size of the database. And so this will increase storage costs. We need more space for backups. There will be longer failure recovery times, more generated WAL, replication traffic, and so on. The memory usage is also something that we have to pay attention to, because we want indexes, ideally we want them to live in RAM, to be like cached and quickly available, but if we have many of them, they will compete for, this RAM will be disputed between other indexes, and also with the table data. So we want to have as many RAM available as we can to to work with Postgres, and if we have many big indexes, it's something we have to care about. Also, we will have slower writes, because that tree structure, we have to maintain those properties of balanced and ordering. So every time we write into a row and we're updating a column that is indexed, we have to update the index as well. And it can be expensive operation, relatively expensive. Sometimes we have to reorder the tree or delete things, and adding it's expensive. And if we have a row that has several indexes, it means that we're updating not only that row, but all the indexes that are there. So if we have, like, for example, 10 indexes on a row, and we update that row, we are actually making the row update plus 10 indexes update. And also, there is more work for the query planner to do, because it will estimate costs for every possible paths for fetching the data. And if we add more indexes, it's more like, it will grow, the number of possible paths grows, and the query planner has more work to do. So now let's talk about some index features, some advanced features that they give us more power to work with indexes. I'm ordering them by usefulness, and I think, and this is a multi-column index, also known as a composite index. It enables us to index more than one column at the same time in the same index. If we contrast this with having multiple indexes, we see how they are useful. For example, in this query, we're adding an index on the A and B columns at the same time. If we had separate indexes and we would do a search on this table, we would first search on the index that has A values, then search on the index that has B values, build bitmaps, and make operations on these bitmaps before we can actually fetch on the heap. So it's a lot of intermediary work that's happening because we have the separate indexes. With a multi-column index, all the information that we need to find where the row is in the same place. So we just go there, search, and fetch on the heap. There is a caveat though. In Postgres 17 and under, we need to follow some prefix rules, which means that when we write a query and a where clause, we need to make sure that the order of the fields here, they have the same prefix as the index definition. So in this example, the column B won't be using the index because it should be prefixed by A. Like this will use the index because both are in the index and they're using the same order. This one will use the index, the second query will also use the index, even though it does not have the B column there, because A is there, but this one will not use the index. This is for Postgres 17. On Postgres 18, we have a new feature called the skip scan that will make that index useful on some scenarios. It's able to use the index for searching for the B column, even if we don't have A here. And this is, it works best when the leading column has low cardinality. For example, countries we have more or less 200, or car makers also in systems we don't usually have many, so we have few distinct values, and it makes a good scenario for skip scan to be used. The partial index is when we reduce the size of when we select only a subset of the table to be indexed. And we do that by adding a where clause on the index definition. This means that we'll only be indexing rows where the status is doing or done. Notice how the where clause here matches the index definition. And this is good because, for example, on a to-do application, let's say we only care about active tasks, and we have millions, like we have like 90% of our rows are already done, are to do. And but we don't care for them now on this example. So why are we going to waste space indexing them? We can just index the doing and done, and then we will have a smaller index. It will mitigate many of the size-related costs that we talked before, and also the tree will be, the height of the tree will be lower. So it's fewer steps to find what we're looking for, and it will make more efficient searches. We also have covering index syntax. This is when, so let's go back to how, a little bit about how the mechanics of indexes work. When we want to find something, we will look on the index and then go to the heap to find the other values that are not indexed. Let's say I have an index on a column name, but I also want to retrieve the age, the email, and other data from some user, but I'm only indexed the name. I have to find the user by name on the tree and then go to the heap to fetch the other data. With this syntax, we can include the other data that's needed on the index itself. This data is only going to be used to be attached to the leaf nodes, so we're not like replicating it in every node of the tree. And it will make it will increase the likelihood of index-only scans happening. And this also greatly improves query efficiency. Also, we have expression indexes. Expression indexes, I'm talking about this function here. It could be also other types of expressions like arithmetic expressions, concatenation expressions. This is a counterexample. This is where we are not going to use the index because we are querying for lower name. Like we are searching for name with the lower function here. Yes, we have an index for name, but it doesn't match exactly this expression, so the index is not going to be used. Postgres can't use the index on these conditions. How we fix it? We use the same function that appears on the where clause on the index definition. Now Postgres can use the index, and this is called an expression index. It's useful for like built-in functions, also user-defined functions. These functions need to be immutable, so we have to take care with date-time functions, for example, because we could be using time-stamped date, and they are mutable, so it would not work for that. But for immutable functions, it works pretty well. And this is just an example of a concatenation expression that we could be using inside the parentheses here of the index definition. Now let's talk a bit about other index types. We talked about B-tree. So far, it's the most useful index. Probably it covers the majority of cases, but for some specific data types and scenarios, there are other index types that also can help us. The first one is the generalized inverted index. This is it's an inverted index, so the closest analogy for this data structure is indexes that we have on the back of books, where we have a term and then all the pages where that term appears. And this is great for composite data such as text, arrays, or JSON. And Postgres has specific access patterns for finding these data types. So we can use it for array with array ops, JSONB, with a vector, etc. Great for full text search as well. The other type is the hash index. This is very similar to hash maps present in programming languages, where we are referencing, where we have a key and a value pair. The key is going to be a 32-bit hash code of the key. We will apply a function and then transform the key into some smaller value. This is great for making these indexes smaller, and they work for every data type you can think of: text, JSON, array. You can index almost everything. The scenarios where we want to use it, it's when we have mostly unique and distinct values in the indexed column, because it's a hash key. Conflicts can happen. Postgres will solve the conflicts for us, but it will hurt the efficiency of the index. And it only supports equality operations. The B tree, it supports not only, the B tree supports equality because it's ordered, right? The B tree is ordered. So it also supports range operations. We can order things using the B tree. Like, let's say we want to find everything that's greater than some data, than some date. We can go on the B tree to the leaf node until we find that date, and then we can just scan forward and we can have a range. But here, no, here is just like, is it equal or not? So we cannot use it for ordering. We cannot do multi-column indexes, and also we cannot enforce uniqueness constraints with hash indexes. But they're great for unique things like UUIDs, URLs. There are several cases where they are useful. The next one is the block range index. This is a very interesting one and a little bit more complicated to explain, but bear with me. This is very useful for situations where we are just appending data to the table, because they work on the assumption that the indexed column has a high correlation with the place where the data is actually stored on this. So for example, if we have time series data, or if we have some logs, and everything is always being appended to the table, we can be sure that we can use this block range index. They are completely different data structure. They are like blocks with ranges of pages, and in each block they have a minimum and maximum value that can be present inside that block. So they can be very small, and these min and max indicators, it's what make them be compact and fast, because we can go to some block and ask, inside these pages, does this value exist? Since we have the min and max, we can skip big chunks of disk space by just looking at this block. The next one is the gist. It's a generalized search tree. It's very useful for geometric types, spatial data. There's a Postgres extension called Postgres that uses them extensively. For range types, they're also useful, and also full text search, they can be used as an alternative to GIN. And they support operations such as contains, is contained, rightmost. It supports different operations than the other indexes that we talked about. The SP-gist is a non-balanced version of the gist. It can be used for like hierarchical data, data where natural clustering is, where you want to do like clustering operations such as phone numbers and like find for by prefix, for example, IP addresses, and several types of hierarchical data like trees, KD trees, radix trees, and it's more efficient than just for certain data distributions. And here I have a quick summary of where to use every index type. The B tree is like general purpose, very flexible, supports equality, range, and ordering operations. The GIN we use for composite data, JSON-B, arrays, and full text search. The hash, it's only for equality, and for long values, like since we're hashing them, we're making them smaller. The BRIN for large tables, super large tables where there's a high correlation between indexed column order and the order where the order used to store things on disk. The gist for geometric data, ranges, and full text, and SP-gist for clustered data, quad trees, and radix trees. If you want to learn more, the Postgres documentation, it's very good. There is a website called Use the Index Look. It's great. It's not Postgres specific, and it goes really deep on the theoretical part of B trees, of when to use composite indexes. I love this website. You should check it. There's a Postgres, there's a blog post I wrote as well with a more extended, more detailed explanations I gave in this talk. In YouTube also there are many great talks, including one by Bruce. And that's it. That's what I have for you. Thanks.
Thank you for the presentation. My question is about PostgreSQL 18 feature that allows to do search with the second column in composite indexes. My question is that if the composite index stores the data first for the first column and then sorts for the second column, how it makes possible to use the search with the second column as well? So what is done differently for this case that it allows?
I'm not sure. To be honest, I don't.
That's why the first column only can have very few unique values. It's actually a really cool idea.
I have also the question about multiple column index, and as you mentioned above, if we have multiple index and on A and B, and the query only on the B, will the planner consider this planner? Maybe skip scan can help them to use it, or will it just reject it at the beginning?
Could you repeat your question, please? I'm not sure I understood it.
If we have a multiple index and the query that uses only the second column, for example, if we have index on A and B, and the query that uses where B is equal to, and so on, will the planner consider this index, multiple column index, somehow, maybe with help of skip scan on B, or will it just reject it at the beginning?
I know we don't have any limitations on making multiple indexes, but maybe there is a trade-off between making a lot of indexes and I want to know when there is a right time to make new indexes. What factor you think when you want making new indexes, when you say yes, we now need that new indexes?
You have to think about query patterns. It usually shows as the application grows, as it's used in different ways, that query patterns will change and maybe your indexes will stop being so effective, and you have to think about how to add more indexes. One common pitfall I used to make a lot is like making indexes based on columns. Like this column I think needs an index, and then you add, in the end you have like hundreds of indexes on your tables, you know. But actually we have to think about the query patterns and the data distribution in the columns, and try to make fewer indexes, like use all of this paraphernalia to build fewer indexes that can serve more queries.